recording. All right. The only problem is I got to put up with that beeping, but that's okay. So, you have stuff you want to cover tonight, or we doing SAT?
Yeah, actually.
Okay, cool.
Okay, so we're going over the limits now.
Ah, cool. You're into calculus.
Super cool. I'm struggling.
Well, I can help. I can help. I can make it easier.
Okay. So, this one, it wants to explain why you can't use substitution to determine the limit.
Okay.
And then it wants to find the limit if it exists.
Okay. Go ahead and give me the function.
Okay, so this is the limit of the square root of x minus 2 as x approaches negative 2.
So x approaches negative 2 or 2?
Negative 2.
Sure. That's it?
That's all it has, yes.
Something wrong here. Because if I do a direct substitution, I get the square root of negative 4, which is an imaginary number. So the limit actually is 2i.
It says that you can't use the and it wants you to find the limit.
Right. Okay. Let me give you a problem. This is the kind of problem you're talking about. If I substitute, I end up with 0 over 0. I don't know what the limit of 0 over 0 is. It's indeterminate. Okay, so I can't solve for the limit by substitution. But I can factor the top into x plus, let me do it the way I teach everybody to do it. X minus 1 times x plus 1. And now I can cancel out the bottom. So I end up with, now it's the limit of x plus 1 as x approaches 1. Now I can substitute, and that's 2. So that's the way you do these limit problems. First of all, let me say something about limit problems. There's only one situation that's difficult, and that's when substitution produces a 0 over 0. If I make that there, now I can solve it by substitution. As x goes to 1, the numerator goes to 0, the denominator goes to 2. Well, the limit of that is 0. So most limit problems can be solved by substitution. If I end up with some number over 0, well, then that's infinity or undefined. So the only thing that presents any problem whatsoever is when I end up with 0 over 0. So all of the difficult ones they give you are going to be 0 over 0 when you do substitute. Okay? So that's why I don't understand this problem.
I don't understand it either.
Doesn't make any sense. So it's possible that we've got miscommunication on somebody's part, but the limit of that as x goes to minus, are you sure it's x going to minus 2 or x going to 2 from the negative side?
Minus 2.
Really?
Yeah, the negative sign comes before the 2.
Okay. Have you studied left and right side limits?
Uh-huh.
Okay. So you know what I'm talking about when I put a negative sign up there. Okay. But you're saying that this is negative 2. Well, don't know what they mean. Let's just skip that one. What's the next one?
So same direction for the limit of 1 over x squared
1 over x squared?
Yeah.
Okay.
As x equals 0.
Okay. What's this going to be? In other words, this is not 0 over 0. So, how are they teaching you to do this without substitution? I don't. Do you have an example of one? I mean, I've studied limits a lot, and I don't have a clue as to what she's doing. This one's infinity. What's that?
Graphing is the one.
Okay. Okay, good idea. This one graphs like this. And we can see what happens as x approaches 0. What is the function?
It continues to go up and up and up and up and up.
Goes to plus infinity. As opposed, this is actually an interesting function. If I had this, the limit doesn't exist.
Yeah.
The reason being is that as I approach 0 from the right, I'm going to positive infinity. As I approach 0 from the left, I'm going to negative infinity. Since they are different, the limit does not exist. As opposed to this one, where when I approach 0 from the right, it goes to positive infinity. When I approach it from the left, it goes to positive infinity. This definitely exists. And it's plus infinity. In other words, this is the first good illustration that I have ever seen with you where we can differentiate between the words does not exist and infinity. They don't mean the same thing. This one truly does not exist. In other words, if a limit is different from the left than the right, it does not exist at that number. But if it's the same, approaching from the left or the right, it does exist, and it's plus infinity.
Okay, I'm still confused about one thing. So why can't we use substitution to do that?
I do not know. You could. You could. I can substitute x equals 0. I get 1 over 0. That's infinity. Now, if I substitute 0 here, I also get infinity. And it's not really infinity. This one really truly does not exist. So maybe that's what she's doing. Maybe that's why she doesn't want you to just substitute it directly. In other words, when you substitute it directly and I call 1 over 0 infinity, that's kind of correct, but not really, because the limit doesn't actually exist at 0. Whereas this one does. Okay, what do you got next? Maybe I can figure out what she's trying to get at.
Okay,
Ones that are tough are stuff like this.
huh?
This one's a tough one.
Yeah.
Why? Because when you substitute, you get 0 over 0.
Yeah, she gave us the formula. She gave us the thing for that.
Okay, and here's the formula. Well, it's the limit of, actually, calculus is a bit strange, and I'll tell you why. There's a real easy way to solve the 0 over 0 problem. But until you've learned how to differentiate and take the derivative, you can't use that rule. There's a real simple rule that says if you take the derivative of the numerator and the derivative of the denominator and reevaluate it, you get your answer. Well, the derivative of sine is cosine. The derivative of x is 1. Cosine of 0 is equal to 1. So the limit of that is 1, based on L'Hopital's rule, which says that if you have an indeterminate, 0 over 0, you can solve it by taking the derivative, the top and bottom. Problem is they can't teach you that before they get to it. And they can't teach you calculus, derivatives, until they've taught you about limits. So it's kind of a catch-22 situation. They don't really have any way of teaching you how to do this problem right here. They just tell you that the limit of that is equal to 1, and then let you go from there. So they give you this as a memorization thing, and then next year when you take calculus, they'll show you how they actually get it. So what is your next problem?
Okay. So the limit of the absolute value of x over x as x approaches 0.
Okay. What do you think it is?
So you have to.
You need to analyze what happens when we approach from the right and what happens when we approach from the left. And are they different?
Yes.
They are different. So therefore, this limit in other words, when I approach it from the right, it goes to plus 1. When I approach it from the left, it goes to minus 1. Since they are not the same, the limit does not exist. Now, if I said this, different story. That is plus 1. If I said this, that's minus 1. I don't quite know how she wants you to do these.
My teacher had a sub tomorrow, so she went over 2 days worth of notes today.
Well, limits really aren't that hard. Usually limits involve factoring. In other words, a typical limit tough problem would be this. Because when I substitute, let's say x goes to minus 1. Okay? When I substitute directly, I get 0 over 0. Like I said, if I get anything but 0 over 0, I pretty much know the answer. But when I substitute and I get 0 over 0, then I have to do more things. Well, again, I can factor it because the top is x minus 1 times x plus 1. The bottom is x plus 1. I can cancel the bottom with that, and now I have just that remaining, and as x goes to minus 1, this whole thing goes to minus 2. So that's a typical limit problem, is one where you can manipulate this to get rid or to change it so that it's not 0 over 0. What else?
This one is the limit of parentheses 4 plus x.
4 plus x?
Yeah. And parentheses squared. Minus 16 over x.
All over x or just the 16?
All over x. Sorry. And x approaches 0.
Okay. We can see this is going to be a 0 over 0 problem. Hold on a minute. I'm thinking. Well, I'm trying to figure out how your teacher would want you to do this. Expanding, yeah, it does help. Let's expand it. Let's multiply that out.
So you get
Now the 16s cancel. I can factor out an x. So I've got x times 8 plus x in the numerator. Got x in the denominator. Now, as x approaches 0, what does this thing go to? We've just got 8 plus x is all we have left.
Yeah, and then you don't have to do anything with the other.
Well, as x goes to 0, this thing approaches 8. So this limit is 8. But I can only get it after algebraically manipulating it, so I don't have 0 over 0 anymore. Okay. What else? It's exciting you're getting into calculus.
Yeah.
Yeah, you're done with pre-calc. Totally. You're going to be doing calculus the rest of this year and all of next year.
It's getting a little bit confusing, yeah.
Well, it is. Limits can be a little different. The concept of limits is new to calculus. In other words, this doesn't exist prior to calculus. When calculus was first discovered, there were a lot of mathematicians that didn't trust it. They didn't believe in it. One of the major theorems of calculus is Raleigh's theorem. Raleigh was a famous mathematician, and he spent his whole life not believing calculus was real. And of course, over the next 200 years, it's turned out that calculus was the most important math development in the history of man.
Crazy to think about. I don't understand how somebody can, like, discover a new math. Like, that's
Yeah, it's not discovery so much as developed. In other words, calculus requires that you view it differently, and this concept of limits is critical to it. Basically, let me give you an example of why limits are important. If I want the area under that curve between this point and this point, we have no way to do that with normal math. Okay, I'm looking for this area. Well, if I break this thing up into a bunch of rectangles and add up all the area of the rectangle, and then I let the width of the rectangles approach 0, I get the area under that graph perfectly. But it requires that concept that this interval right here, we'll call it Z, has to approach 0. In other words, if I draw rectangles that are each one length in width, then I don't get the true area. I get a rectangle that just approximates it. But when I'm finished, if I let the width of each rectangle go to 0, meaning I have an infinite number of rectangles in there, as the width of each rectangle gets smaller and smaller, the number of rectangles I can fit in there gets larger and larger. But you can kind of see as the rectangles get really, really close to 0, the top fits the curve perfect. And so the concept is, if I want the area under this curve, I'm going to add up all the rectangles, and I'm going to let the width of each rectangle go to 0.
okay.
And that's calculus. That's why we need to learn limits, is because calculus is always assuming that we're letting one of the dimensions go to 0, approach 0. Can't actually go to 0, but it's a concept. This is a concept that Raleigh didn't trust. It's not like most mathematics that you've ever had, where you let something approach 0. All right, I don't want to get ahead of you on this, So let's stick with just the limit problems, but this is why all calculus classes start out with limits, because you can't really understand calculus until you understand the concept of limits. Now maybe she wanted you, that first question, as x goes to minus 2. Well, if we graph that, this graph looks like this. So I can tell that as x goes to minus 2, it doesn't approach anything. Minus 2 is way over here. It's not in other words, it does not exist. I said originally that it was 4i, or 2i, because I brought imaginary numbers into it. Well, let's leave imaginary numbers out of it. If I look at it graphically, it doesn't exist because x never does approach minus 2. Function starts there and goes up and to the right. X has to be greater than or equal to 2. So perhaps that was her purpose in this. She wanted you to answer it graphically.
That makes sense.
Probably. I don't like that, but I don't like this problem as a teaching limits. In other words, most thing ends up with a number over 0, that's infinity, or 0 over a number, that's 0. So most limits are either infinity, 0, or does not exist. But the only difficult ones is when you substitute and you get 0 over 0. And then you have to do a lot of work to figure out what the limit is.
Okay, yeah, because, she's talking about that today.
Yeah. Any other kind of a limit problem is a no-brainer.
Yeah.
Well, almost. In other words, there is the question of, are these different? And she doesn't even want to talk about that, I guarantee you. In other words, this one actually does exist, and it's infinity. This one truly does not exist, because the limit from the left and the right are different. But that's a distinction that they will rarely tell you about. My calculus book does mention this example, and it does say they can make no claim to this limit, the top one, but they can say this one exists for sure. And that's the difference between infinity and does not exist. Not exactly the same. And up until now, they've been telling you that they're the same. So, what else you got?
Okay, so this one wants,
your solution is going to be factoring almost always. Let me just tell you that, since we only got 5 minutes.
Okay. I think we can do one of these.
Okay.
So this one is to find out the limit graphically.
Okay.
And it's the sine of x.
Sine of x?
Yeah. Over 2x squared minus x.
As x goes to 0. Okay. Let's factor the bottom. Correct? Okay. Now they've also told you to memorize what the limit of sine of x over x is. Correct? They've told you that that's 1. Well, this is sine of x over x times 1 over 2x minus 1. Well, now I can do a direct substitution, because I know that that goes to 1. What's this go to when x is 0? Substitute it. Negative 1. So if this goes to 1 and this goes to negative 1, then the whole thing goes to negative 1.
Yeah.
Now, she wanted you to do this graphically?
Yeah, I can do that. That's
Okay, well, you can plug that. I could plug that into Wolfram Alpha and look at the graph. That's not going to be easy to graph manually, but your calculator can certainly do it. And she's going to, graphically, we'll see that as x approaches 0, y approaches minus 1. That's what you'll see on the graph. It's just like the graph of sine of x over x, the limit of this. Well, if you look at it graphically, it looks like this. Well, so we can see that as x goes to 0, graphically it certainly appears that that limit goes to 1. But you should also be careful, that's not confirmation of it, because we can't really see the graph. We think we can, but my math books say that just because, in other words, when my calculus book looks at this problem right here, and they show you the graph, their statement is, the graph would support the fact that the limit appears to go to 1.
Yeah.
But that's all they would say. They would not say it proves it.
You have to prove it algebraically, right?
Yeah, you have to do a lot of work to solve that. There's a way to do it without using L'Hopital's rule that's extremely complicated, and that would be crazy of them to teach that to you at this step. But so they start off calculus by having you memorize that that's 1. And then any problem that uses anything like that, such as this problem here, you know that this one goes to 1, and this one you can evaluate by substitution. So, but the key here is always going to be factoring. In other words, any of these problems where direct substitution results in 0 over 0, factoring is your next step. Once you factor, you'll be able to split it apart, and then it won't be 0 over 0 anymore, like we did here.
Factoring, right?
What's that?
Usually you just have to factor it, right?
Yes, yes. Almost all of the problems on limits that are tough are going to be solvable by factoring or being able to pull out a sine x over x, something like that. In other words, factoring alone didn't do it. Because if I didn't know sine x over x went to 1, I would still have 0 over 0. But the fact that I know sine x over x goes to 1, I can replace that with a big 1, and then I can actually substitute over here. All right. You got any more that give you trouble? I don't have anything till 7:30, so if you got another one you want to talk about, I got time.
I think I'm just going to have to wait after about that substitution thing, because I still don't really understand.
What is it you're not understanding?
Just why you can't use substitution to find the limit of something.
Because you get 0 over 0.
That's the only reason?
That's the only reason. That is called indeterminate. We don't know what that is. We don't know what 0 divided by 0 is. That's not necessarily 0. It can be 2. It can be 7. It could be infinity. We have no idea. It's called an indeterminate. Okay? So when you do direct substitution and you get 0 over 0, you can't go any further than that until you either factor or get something, somehow manipulate it so you no longer get 0 over 0. Okay? And usually that something is factoring. In other words, the classic situation is this one that I keep putting up there. What does this do as x goes to 0? Well, as x goes to 1. Well, if I do a direct substitution, I get 0 over 0, right?
Yeah.
But if I factor the top into x minus 1 times x plus 1, and then put this down there, well, now I can cancel that with that, and what I really have is x plus 1. Now I can substitute. Goes to 2.
Okay. I
So,
just don't understand one then where it says the square root of x minus 2.
uh-huh.
Why can't you substitute that? Because that doesn't give you 0.
No, but it gives you the square root of a negative number.
Always? Oh, yeah.
Well, no, in this case.
Well, yeah, when you put it as a negative 2, it gives you...
Right, because now I'm taking the square root of negative 4. Well, I don't know what that limit is.
You can tell i's in the...
No, you don't, never. I mean, maybe in sixth year calculus, you bring in the imaginary number, but not in limits, you don't. That's why I was puzzled by this question. But this question does allow you to look at it graphically, and you can see that x never approaches minus 2.
Yeah.
So that alone tells you that that does not exist. If x never approaches minus 2, then it can't exist.
All right.
All right?
These are seeming like they're okay.
Yeah, if you treat them like algebra problems, you'll be fine. In other words, the only ones that are going to be tough is when you get 0 over 0, and just factor whatever you can factor and cancel with the denominator when you can cancel, and then whatever you have left, you'll be able to substitute and you'll get a real number. You won't get 0 over 0. All right. Sarah, I will talk to you next Tuesday.
Thank you.
All right, bye-bye.